Hey chemists. So today I'm going to go over the simulation part of the last lab, molecular bonding, geometry, and polarity. So if my environment and sound looks different, that's because I moved over the weekend. I'm very tired, but we will do this. All right. So molecular bonding and geometry and polarity. So this is kind of going back to chapter 7 material, right? Counting electron domains, molecular domains, Lewis structures, all those steps. So hopefully you've got that down from the midterm that we took last week. And this lab requires 2 different simulations, and I believe they work on my computer, and I have one of them here. So let's see. Okay, so this is what essentially you're doing. You're doing a couple different activities with different simulations. First, you're going to practice drawing Lewis structures again, because remember, with molecular geometry and polarity, you need to start with determining Lewis structures. So hopefully you've got that scaled down, completing octet rules and counting valence electrons. Hopefully you've got that down. Activity 2, we will be looking at molecular geometry of different numbers of molecular domains and electron domains, right? And look at the bond angles. So this program will spit out this information for us, and we'll record what it says. And then we'll start looking at polarity. We'll look at polarity of these molecules, and so that will require us to add an electronegativity table. And again, think about our shapes and bond angles, and think about how those vectors cancel out. All right, so I'm going to try my best not to give you any answers, and just instead go through the simulation as if I was just your lab partner. Yeah, but I will try to be very clear in what I'm doing in the simulation and what box that corresponds to. Okay. All right, so first activity, drawing Lewis structures. You can do this on your own. So here are the steps, 5 steps. All right, do the Lewis structures for these. Some of them may break the octet rule, FYI, so we have some exceptions in there. All right, so this is activity 2, VSEPR and predicting molecular geometry. So I have this simulation up. Right, okay, so there we go. So this simulation is pretty cool. You can like add bonds and stuff, right? Or lone pairs. We can just like add a bunch of stuff, and it will simulate what it would, a molecule with, a triple bond, a double bond, a lone pair, and a single bond, what that would look like, right? So we can either have the lone pair there or take it away. We can show bond angles, which is pretty cool, all right? And then it'll also name it for us. Oh, okay, so this whatever thing I drew right here has a trigonal bipyramid, electron geometry, and a seesaw molecular geometry, right? So maybe I'll take away the bond angle, see? So you can kind of see that it is the trigonal bipyramid. This is, this is the axial, right? And then if I take away that lone pair, you can clearly see we're not changing the structure at all, right? We're just covering up that lone pair and ignoring it and just looking at the bonds, and you see that it's a seesaw shape. See? Seesaw. Okay. All right, so let's start over. What are we doing? Okay. So let's fill out table 2, number of electron domains and electronic geometry. So thankfully, this program will give us the electron geometry and the different, as we add electron domains. So as we add electron domains, let's just add single bonds to this. So right now, I'm going to make this bigger so you can see it. We're just filling out this table. So it has 2 electron domains and it's linear, right? So that's this molecule, this shape right here. Oh, and so we can give it an electron domain. It's telling us that it's linear and that the bond angle is 180 degrees. Right, so that's the first one. That's already filled out for us. All right, so let's add an electron domain for 3. This is with 3 electron domains, so you can write down these answers. You probably already know these names. You should know these names and bond angles. All right. Okay, so let's move on to 4 electron domains. Again, I'm just going to add another single bond. All right, so this is what 4 electron domains looks like. Oh, look, I can like distort it if I want. That's kind of cool. All right. So you can see, I've talked about, tetrahedral shapes before. So now you can really see it in 3D. And see how like, okay, I have this arm pointing up, or I can like rotate the whole molecule and have this arm facing up, but it still looks the same. Like no matter which arm is facing up, it will always have like this triangle base and then one thing sticking up, no matter like which one I choose. It will always look the same. Like my caltrop story. I love that story. All right, let's add what, 5 electron domains? There we go. Oh, this one has note the bond angles. So here's this view. These 2 bonds are going up and down, while these other 3 kind of form a triangle. So there's some bonds, and then here we're looking down on those up and down atoms, the axial atoms. All right, and so here are the other bond angles. Here, it's got to see both right there. That's kind of hard to see though. There, okay. So that's 5 electron domains. All right, and then finally 6. Oh, this is 6 electron domains. That name is octahedral, and then I can rotate it so you can see all the bond angles, but it looks like they're all the same. Okay, so we looked at these different molecules with different number of electron domains, but we only added single bonds. So now the next part of this activity is to look at electronic geometries and molecular geometries. So that's what this check mark is. I can, check this, and now it will give me the molecular geometry and electron geometry, because this is important because now we're going to start adding lone pairs to these molecules. So before I just added single bonds, let's now add lone pairs. So let's just start over, remove all. All right, so we're going to go through this table again. So this first one, let's highlight this. Can I highlight it? So we're going to do the first one. So we want to add a total of 2 electron domains where 2 of them are bonding pairs and 2 of them are non-bonding pairs. So non-bonding just means lone pair. So this third column is just telling us how many lone pairs should I add to this molecule. So in this first row, I'm going to add just 2 bonding pairs. All right, and so hopefully that'll give you a molecular geometry. Right? Oh, does it want bond angles? No, it doesn't. All right, so we have no lone pairs. So this is actually the same. This molecule has the same electron geometry and molecular geometry because there's no lone pairs. Okay. So then for the next one, we want 3 electron domains where 3 of them are bonding pairs and 0 of them are non-bonding pairs. So again, no lone pairs. So I'm going to add my 3 bonding pairs right there. And there are those names. Hopefully you can see that. Yeah, probably. Okay. And then the next one, we want 3 electron domains where 2 of them are bonding pairs, 1 of them is a non-bonding pair. So I'm just going to start over and say, okay, 2 bonds, 1 lone pair. All right, and so there are those shapes. Oop. Those shapes for you. Okay, and then the next one. So 4 bonds, 0 lone pairs. All right, the next one is 4 electron domains. 3 of them are bond pairs. 1 of them is a non-bonding pair. So I'm going to just start over. 3 bond pairs, 1, 2, 3, and then 1 lone pair or non-bonding pair. Cool. All right. Now the next one. Again, we're still under 4 electron domains, but remember, every time we're just like adding a lone pair. So 2 bond pairs, 2 lone pairs. Oh, here's my cat. Do you want to meet her? This is probably one of the last videos I'll make. So here's my cat. Don't come up here. Oh, geez. Okay. Okay. Sorry about that. So 4 electron domains. This is 2 bond pairs, 2 lone pairs. All right, so now let's do 5, all the different combinations under 5 electron domains. So we want to do just 5 bond pairs, no lone pairs. 1, 2, 3, 4, 5. Okay, so there are those names for you. I'll rotate it. You can see all the bond angles. All right, and the next one is 4 bond pairs, 1 lone pair. So 1, 2, 3, 4, 1 lone pair. So see the location of that lone pair. All right, so remember like our axial position atoms that the lone pair will go in the equatorial position. So in 5 electron domains, it's very important where you put that lone pair. Okay. All right, and notice see how the number of bond pairs and the number of non-bonding pairs, so lone pairs, how these two numbers will always add up to the number of electron domains. That's interesting. Okay. And then next we're still in 5 electron domains, but we want 3 bonding pairs, 1, 2, 3, and 2 lone pairs. So 1, 2. I think it's so cute how it rearranges itself. All right, there are our lone pairs. I can get rid of the lone pairs, and so you can really see the molecular geometry if I like remove those lone pairs, and you can see how those lone pairs influence the bond angles. Right. Okay. Next so now it's 5 electron domains of 5, 2 bonding pairs, 3 non-bonding. So 1, 2, 1, 2, 3. Oh wow, this one's fun looking. All right, I can take away those lone pairs so you can see what that looks like. But really, those lone pairs do exist. Okay. All right, so now 6 electron domains. So first one is just 6 and 0 lone pairs. You know what the shape is. So 1, 2, 3, 4, 5, 6. So octahedral, no lone pairs. Oops. Okay. Next is 5 and 1. So 1, 2, 3, 4, 5 bonds, 1 lone pair. It's like a recipe. It's like this table's giving me a recipe to, you know, like 5 pinches of that, 1 cup of that. So there's that shape. And then, so the last one is 4 bond pairs, 2 lone pairs. So 1, 2, 3, 4 bonds, 2 lone pairs. 1, 2. Cool. So see where those 2 lone pairs orient themselves to maximize that space between them. So that second lone pair won't go here, essentially, is what I'm saying. So see that shape? Here, I'll take away the lone pair so you can really see it. All right? Okay. All right. So then work through these questions, and I will videotape the next part of the simulation. All right, so let's explore the last simulation, which has to do with polarity and overall molecule polarity. All right, so this simulation allows us to change, to look at this like 2 atom molecule example. And we can change the electronegativities of atom A and atom B. So we can think of A and B as just like a bond. So if I make both of the atoms the same electronegativity, so in this case, like I have it less. Both atoms have a less, or like, you know, the same magnitude of electronegativity. So you can see the overall bond dipole arrow is not there. Versus if I make them different, like I'll make A have a less electronegative, be a less electronegative atom, and B a more electronegative atom, you see this creation of a bond dipole. So see where the plus sign of the bond dipole is and where the arrow points. The arrow always points to the more electronegative atom. So if I have it like this, where B is more electronegative, see where the arrow is pointing. And then if I switched it, like let's say I made B less electronegative and A more electronegative, you see now the location of the arrow has changed. All right, so we can also look at partial charges. So that'll tell us too, see how the arrow and the charge, the arrow always points to the negative charge. So you can see if I switch it, I'll switch the location. If I make them the same electronegativity, everything disappears. And so you can think that this would be a non-polar molecule. Ooh, we can look at bond character. This is non-polar. So since the electronegativities are the same, this is more of a covalent bond versus if I start to increase, look at that, look how cool that is. Increase the electronegativity difference. Now it's saying that this molecule has more ionic character. That's pretty cool. But like if I make them both the same, like let's say I just put them like smack dab in the middle. Isn't that pretty cool? Okay. Okay. So talk about, right. Okay. So hopefully, yeah, that now you can answer question 4. So if I just like play around with here and make them different. So now A and B are the same. Maybe I'll put A like 1 tick up, maybe another tick up, maybe like halfway, you know. If I like switch B all the way to more electronegative, I'll like switch the arrow. See, so less, same, more. Cool. All right. So that's showing different bond character and changing the electronegativities of A and B. Now, so when we change the different electronegativities and we see the presence or absence of a bond dipole, right? So here you see a bond dipole. If I make them the same, there's no bond dipole. What does that mean for a molecule? Well, if there is a dipole present, you can kind of think of the molecule like a magnet. If I turned on an electric field, then those dipoles would want to arrange themselves into that electric field. So that's what this part, question 5, has to do with. Now let's put these molecules in an electric field. So right now I don't have any electronegativity difference. So let's make a dipole. All right. So let's turn on the electric field with this button and see what happens. Oh, cool. All right. So let's try that again. So I'm going to move the molecule. I'm going to keep the arrow there so you can kind of see like where are electrons on this molecule. Turn on the electric field. Oop. Cool. So note which side, where the arrow is pointing, and the signs of the plates of our electric field. Right? So our arrow is pointing to the positive side because that arrow indicates the location of the negative charge. Right? Okay. So that means if I like switched this up and made the arrow point the other way, right? Okay, wait. So the arrow is pointing there. So let's make the arrow point a different direction, like this direction. We should be able to get the molecule to spin the other way. Is that right? Yeah, look at that. All right, so now A is pointing to the positive plate, but the electric field only cares about these partial charges. All right, so cool. All right, so let's keep going. Oh wait, I didn't answer this question. Is there any relationship between magnitude of bond dipole and the effect on the electric field? All right, so let's make the arrow really big and see what happens. All right. So I'll just put it there and see what happens. Because I know it's going to turn, but okay. So this is what happens when the arrow is really big. Let's see if I can't make like the arrow really small. Let me get smaller. All right, so there's still a bond dipole, but it's just smaller. So let's see. All right, so this is with a small magnitude bond dipole. I'll go back to a really large one. So, oop. All right, so the speed in which the molecule rotates is definitely affected. All right, so hopefully you can explain that. Okay, so let's look at a different type of molecule. This is only for an AB type molecule. Let's look at one with three atoms. Okay, so now that we have 3 atoms, we can kind of we have to think of vectors and think about the shape of the molecule and if those bond dipole vectors can cancel out. So we want to go through this list. Let's first make these flat molecules. All right. And so actually in these pictures, you can do you can do without the simulation right now. You can fill this out. Which atom is the most electronegative? It might be multiple of them. So in molecule, this first one, ABC, the arrow is pointing to the most electronegative element. So in this case, I'll just tell you that it's both B and, no, wait, positive and positive. C should be the most electronegative element. Because in this picture, it's saying A is more electronegative than, or sorry, is less electronegative than B. B is the more electronegative element between A and B. And then between B and C, C is more electronegative than B. So in this molecule, this first one, C is the most electronegative. All right, so I'm gonna make this molecule. I have to move some stuff around. All right. Okay, so I made it flat. It's hard to make it like completely 180 degrees. Okay, so if C is the most electronegative, we have to think, is this molecule polar or non-polar? So ask yourself, do these arrows cancel out? I always like to think, you think of like a tire. Let's say we put a tire, like B is a tire. And so this A molecule is pushing on the tire. And then the A atom is pushing on the tire. And then the C atom is pulling on the tire. Will the tire overall move? I would say yes, because those arrows are both pointing in one direction. They don't cancel each other out. So I would predict yes, this molecule is polar. All right, so I don't have this drawn right now. So we want to draw the molecule. It looks like this. So now it matches. All right, so I would predict, oh crap, I messed up. Okay. I would predict, yeah, this molecule is going to move because these arrows are all pointing in one direction. They're not canceling out. This molecule is polar, so it should be affected by the electric field. So let's turn that on. Yep, look at that. Oop, oop, oop. And then, so here are the individual bond dipoles. So you can also draw the sum of all those bond dipoles, which will give you the molecular dipole. And it tells you the same thing, that these two arrows don't cancel each other out. And then overall, the molecule has like one big dipole arrow. Okay, let's do the next one. So we have A, B, and C. Which atom is the most electronegative? So again, arrow always points to the most electronegative atom. So I'm going to draw this. It should look like the, oops, turn you off. There, maybe, I don't know. Okay, so here is that second molecule. So I have two dipole arrows, and then you can see, okay, they're the bond dipoles, and then the overall molecular dipole, it should cancel in theory, but it's hard to do. So write your prediction for whether these bond dipoles cancel, or whether the molecule is overall polar or non-polar, and whether it is affected by the electric field. All right, so there I turned the electric field on. You can see that it's actually moving really, really slowly, and that's because I can't get rid of the molecular dipole. It's because I can't get these atoms like completely 180 degrees from one another. But in theory, this molecule should not be affected by the electric field. If I tried like really hard to get rid of, see, I can't get rid of it. Ah, oh crap, I messed up. Ah, right there. Okay, I did it. I think so. So now I think if I turned it on, it should, nope, it's still moving. Look at that. Made it worse. But in theory, this one shouldn't move. Okay, so then the next molecule, I actually have to bend it. So I'm gonna reset it. Okay, so let's make our picture look like that. Okay, so A and C. So which is the most electronegative? Again, arrows pointing to the more electronegative atom. So I'm going to change it up like this. Here we go. All right, so predict the most electronegative atom. Let's stick that molecular dipole on there. So I predict this molecule is polar, and so it should be affected by the electric field. Oops. See? Here you go. That way. Hold this way. Cool. Right. And so see how that molecular dipole, how the arrow is aligned to the sign of the plates. All right, so the next one, A, B, and C. So this again, oh no, we want it to go this way. We want us to make it like that. Okay, so now so now the arrows need to point to B. There we go. Okay, so there's our so those are just our individual bond dipoles. If we make B more electronegative than A and C, and then here is our overall dipole, right? So predict whether that's polar or nonpolar. And then now let's test our molecule with the field. There we go. Look at that. I'll take away the molecular dipole. All right. Okay, so that's how that one works. And then finally, the last one, A, B, and C. Let's turn that off. A, B, and C, so it wants it like this, but it doesn't want any arrows. So that means all A, B, and C should have all the same electronegativity. So I can either make them all like this, or maybe I could do like this. It doesn't matter, as long as they're all the same. Okay, so here are the bond dipoles. Here's the overall molecular dipole. If you want to see partial charges, there they are. All right, and then so there's an absence of arrows and partial charges. So if I turn on the electric field, that's what happens when there are no arrows. Cool. All right, let's keep going. Okay, so the last part of this lab is to fill out this table using the simulation, and then there's some questions here using a kit. So you'll just have to do this on your own time to represent these different compounds. So let's just fill out this table first. So just pause the video, fill out your Lewis structure and your predicted molecular geometries, and then check or like predict whether it'll be a polar molecule or nonpolar. So after you do that, I will show you the real molecule models and show you whether there is a molecular dipole or not with this real molecules tab. All right, so once you've done that, then restart the video and I'll show the answers. Okay, so this first molecule is nitrogen, and so here is what nitrogen looks like. See, I have bond dipoles on and molecular dipoles. So if you see an arrow, if you see a yellow arrow, that means that there is a molecular dipole and the molecule is polar. But you see that there's none, so diatomic nitrogen is in fact nonpolar. Okay, so let's do a polar example. So water, here, water. So this is what water looks like. All right, so here are the two bond dipoles for water, and then I can, oh my gosh, stop being weird. Turn on the molecular dipole, and so there is an overall arrow, yellow arrow there, so this molecule is polar. All right, BF4, or BF3, all right, there's BF3. Here are the bond dipoles, and then here is the molecular dipole. There is none. They cancel. HCN. Here we go. So here are the molecular dipoles. You see those? See the gray arrows? Kind of hard to see. You see the gray arrows? There's a bigger arrow. No, it's really hard to see. There's a small arrow here and then a bigger arrow here. So because this is the molecular dipole is like the net dipole of the whole thing, there's an overall molecular dipole for this atom or for this molecule. All right, and the last one, CH2F2. There we go. So here I'll show you the bond dipoles first. So you see, fluorine's much more electronegative than hydrogen. So the bond dipole between carbon and fluorine is much larger than the bond dipole between carbon and hydrogen. You can just see like there's actually none. Usually we say that CH bonds are nonpolar and it's purely covalent. So there's really an absence of an arrow between carbon and hydrogen. And then, so you'll see how those arrows cancel or don't cancel. All right, and so there's the overall bond dipole for CH2F2. All right, so I think that concludes it for the simulation. All right, that's it.